Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. We're from Group 6 of Computational Thinking. We are people from Trakakayan that they want to present about our case study, which is about smart building analysis. Now on to Aji.
For the description and context, a small building has been built with sensors that allow for the monitoring and control of its overall energy consumption. These sensors are able to detect conditions of the environment in and out of the building, conditions such as outside weather, temperature, and even amount of people that inside the building at given any time. Aside from this sensor, this smart building is also able to control systems inside the building, such as the lighting, electronic applicants, and HVAC system. Description for the problem. The operator of the building wants to utilize the sensor and system built into the smart building to its fullest extent by using them to achieve the following goals. To keep operational costs as low as possible, to minimize the impact of the building on the environment, and to ensure the comfort for the employees inside the building. Next, sorry. Okay, for the description and challenges, there are multiple different challenges that has been identified that needs to be solved by given solution. For once is electrical applicants are turned on despite no usage, and usage of the building varies during the day, specifically peak hour. Outside weather affect temperature and lighting requirements in the building. Conflict requirement as these variables interact with each other, and then employee comfort varies between subjective taste combined with previous variable.
Let's continue the decomposition of the problem. So first of all, the goal is to be cost efficient, sustainable, and comfortable. Now, second, we go to the challenges, which is the electricity wastage, the varying occupation levels, varying weather condition, and interconnected variables. Now, the indicators of success is the decrease in electricity usage as compared before the implementation of the solution. And also, the consequences of this problem is actually the decrease in the efficiency of workers working inside the smart building, and also will have a larger cost the day-to-day operation of the building. The defining non-quantitative goal is the employee comfortability, subjective to each individual. Hence, this comfortability will be measured on temperature inside the building, and also the ability for worker to work productive effectively. And now, the defining non-quantitative problem is actually the energy cost, which interplays with all of the other challenges, which might not follow a certain trend, one way or the other. The solution needs to factor all variables and produce a value for energy cost. Next. Now, the pattern recognition we have, first of all, is the peak hours. There might be a consistent pattern for the numbers of employees working during the certain hours of the day. This pattern actually can be used to optimize the electricity and the HVAC usage by manipulating it with respect to the expected number of people working at the building at that time. Next. Now we have the second pattern recognition, which is the weather. So the weather conditions outside the building could also affect the usage of lighting inside the building. For example, like sunny days will let in more natural sunlight that can allow less lighting that is required in the areas of the smart building. On the other hand, the rainy weather can also increase the lighting demand throughout the smart building. Next. Now we have the third pattern recognition, which is the temperature. So the external temperature of the building can play a role in the demand for air conditioning inside the smart building. A pattern might arise where the HVAC usage decreases during cooler days while the HVAC demand increases during the hotter days. Next, Gavino.
In this slide, I will explain abstraction. The problem can be divided into three distinct parts of the three challenges. One part to control the usage of electronics throughout the building can be tied to the number of occupants. One part to control the HVAC system, which can be tied to the temperature outside, and one part to control the lighting, which can be tied to the amount of natural light available to illuminate the building. All of these solutions can be combined to get a value for the estimated power usage of the building at a given time during any condition. Next. And this is the the sample data representation. In the left is office occupancy percentage versus hours, and in the right temperature versus hour. Next. In the slide is humidity percentage versus hour. Next. And in this slide is comfort level percentage versus hours. Next. And in this slide, the last one is light level versus hours. Solution outline. We use the algorithmic design paradigm of divide and conquer, where the challenges are addressed individually before all of it is combined at the end. For both of the occupancy and temperature problems, the brute force method is used as a check of each range is sufficient enough to produce an output. To solve the lighting problem, the linear search algorithm is used by assigning values into the weather condition, having the input be the target value being searched and looping until the target value is found. The result of each individual algorithms will produce an output from one of three levels: low, medium, high, and a value added onto a list, where the value of the final list will determine the amount of power allocated to the smart building. Next, Raihan.
So for the flowchart, it starts here, where another separate list will be created called energy. And the divide and conquer can be seen here, where the three separate problems are dealt with independently before being combined at the end. So for the first problem, is the percentage of occupancy. It starts with an input where the occupancy becomes OCC, and using brute force, it checks if the OCC is between 0 to 50%, between 50 to 75%, and over 75%. And if it lies above any of the ranges, it will send the power sent according to the range. It will print according to the range and will add a value. This value will be added to the energy list created here, and in the end, the total of the value will be added, and that will be the amount of power supplied to the building. So for the second one, is for the weather. Here, instead of brute force, we used the linear search algorithm. So the input here is either 1, 2, or 3, where 1 is sunny, 2 is cloudy, and 3 is rainy. And then the list is made for 1, 2, and 3, and the target value is the one from the input. Here, the linear search is done 3 times, where it is done in the order of the signed list 1, 2, or 3. So say if it's a rainy day, it will loop from here, where it says no, and then it goes to the next one, where it's no, and then finally here, where we'll go through and adding 3 to the energy list. For the temperature, there will be an input temperature, it goes to temp, and again, it's using the brute force method, where we'll check for each range. Here it checks from 25 degrees Celsius below, down to 30 degrees, and then 30 degrees above. Again, it will print the energy to the system, and the value added to the energy list. All of this will be combined here, where the sum total of the energy list is created equals to total, and then this total is again used by brute force, being checked through the range, less than or equal to 3, less than more than or equal to 4, and less than or equal to 6, and then more than or equal to 7. From here, it will print the energy used for the building, and then it will allocate the amount of energy needed for the entire building for that specific time of day. Here's the pseudocode.
Okay, this is the algorithm pseudocode for occupancy. And as you can see, it's get input of the occupancy and assign it as OCC, and you can see it by yourself. Next. And then this one is pseudocode for the weather. The first is set list of energy, and then obtain value of 1, 2, or 3 as target, and then you can see the rest. Next. The last one is the pseudocode for the temperature. First, get the temperature and assign it as temp, and then set different range for different HVAC level, and then you can see it yourself again. Okay, next. Big O analysis. Jordan.
So for the Big O analysis, basically all of them is, since Big O is like the analysis of the longest possible like possibility of how long it can be done, all of them is basically constant, even though it's brute force, because it has the same, all of them has like only 3 conditions, basically, and thus at max it can only do 3 of them. Like even though there's more input data, it doesn't like, it's always going to be a fixed amount of time, because it doesn't actually increase in like the increase of parameters doesn't actually increase the amount of like checks and conditions. So thus the entire system, it operates at a O1, aka constant. And then that's basically it. Thank you all for listening to our presentation. I hope you were interested in our solution to this case study. Thank you.
Now there's a test run.
Oh yeah.
So using the sample data from the given sample, if there was a test done on 12 p.m. on a cloudy Thursday, these will be the values of the data, and the output will be this, where the result that will be that the building be given a higher amount of energy. Yeah. Thank you for listening.